Okay, YouTube is live.
Okay. Hello, everyone, and welcome to our series on seminars on non-Hermitian physics. Today, we are happy to have Professor Wiersig from the Otto von Guerricke Universität in Magdeburg. And before I present him, I have some house rules. First of all, we would want you to know that all the talks are recorded and are made available on YouTube for everyone to watch later. We kindly ask you to switch off your cameras and microphones during the talk, but we will have a Q&A session after, and you can just use the raise hand functionality of Zoom or type your question in the chat, and we will allow you to unmute and start your video and ask your question to the speaker. If you are following us on YouTube, you can just type your question in the chat and we will pass it over. Before we start, our next talk will be next week on the 13th of December by Professor Benedetta Flebus on non-Hermitian physics in magnetic systems. And today we have Professor Wiersig, just to give like a brief bio. He got his PhD at the Bremen University. Then he went for a postdoc at the Queen Mary and Westfield College in London. He was a guest researcher at the Max Planck for the physics of complex systems in Dresden. And after that, he went for a period as a researcher again at the Bremen University, and since 2008, he's in Magdeburg. He will talk about non-Hermitian optics in microcavities. Professor Jan, it's a pleasure to have you. You can share your screen, please. And maybe
Yes, I'm muted now. Now you should see it.
Yes, we see it.
Okay, let me just move this here away. Okay, so yeah, thank you very much for this kind introduction and for inviting me. I'm at the Otto von Guerricke University, that's how it's pronounced. The Otto von Guerricke is the guy with the half spheres with the vacuum and the horses, which I try to pull these half spheres. So my talk, I will speak about non-Hermitian optics or photonics in microcavities, and I will cover exceptional points, obviously. And I will speak also a little bit about these applications, exceptional-based, point-based sensors. Here's an outline of the talk. So first, an introduction where I introduce it to the field of microcavities briefly, to exceptional point and non-Hermitian physics. And then I will explain in the second part how you can create exceptional points in what is called whispering gallery microcavities. And at the end, I will ask the question of how strong an exception point is. Okay, so first the introduction. So the simplest optical microcavity that you can imagine is such a micro disk. Yeah, the boundary is a circle when you look from the top, and there you can, in such a cavity, you can confine light. Yeah, to a small room here, about 2 micrometers or even less. And the light confinement is just by total internal reflection. Yeah, you can imagine a light ray, which is just impinging on the boundary and then being reflected, as long as the angle of incidence is large enough. Yeah, the corresponding solutions of Maxwell equations with harmonic time dependence, that are the optical modes, and they often look like this here. Yeah, so they are called and also whispering gallery modes. And the name Whispering Gallery comes from the Whispering Gallery in the St. Paul's Cathedral in London. There are also other buildings where you can have this. And the idea is very simple. You stay somewhere here and then you say something. And then the sound waves, they travel along the boundary like this electromagnetic wave here. And then someone else can hear it far away. Yeah. So I can recommend to try this. It's really impressive. Such a simple effect, but quite impressive. Okay, so these optical modes, even so I said total internal reflection, they have a finite lifetime. That's because total internal reflection at the curved boundary is never total. Yeah, they're always something which you can interpret as a tunneling effect. that let the light go out a little bit. And so they have a finite lifetime, tau. And in optics, usually people express this with a quality factor. The quality factor is frequency, the resonant frequency, omega times the lifetime. That's a dimensionless number. And usually the experimentalists put a lot of effort to have a large Q factor. Large Q factor you need, for instance, when you want to use such a microcavity as a resonator for a micro laser, because you want to have that the photons stay in the cavity for a long time, such that it can efficiently contribute to stimulated emission. There are many other applications. Here's just a non-complete list. So single photon sources, filters, sensors, low power parametric processes like second harmonic generation, and so on, and cavity optomechanics, and much more. There are other kinds of whispering cavities, such as microspheres and microtoroids. I think you can imagine how the light also travels there along the boundary, here, for instance. And then there are also what is called band gap microcavities. So, for instance, such a photonic crystal here, where you generate a periodic structure such that it creates a band gap, similar than the band gap for electrons in a semiconductor. And you can do this here in 2D, 3D, and here is effectively 1D. So this is a micro pillar where you have, maybe difficult to see, hope you see it. There's a periodic arrangement of layers of different material with a different refractive index, and this generates also a band gap. So in this talk, I will focus here on these whispering Guerricke cavities. Even so, we also look at these kind of cavities for different purposes. Okay. Now, our group is interested in looking at deformed or perturbed cavities. So why is that? There are several good reasons for deforming or perturbing a cavity. For instance, if you deform such a microdisc cavity, then the light ray dynamics becomes at least partially chaotic. So you can study the system's ray wave correspondence or quantum classical correspondence if you want. And this for open systems, right? Because you have light escapes, you can measure it experimentally very easily. Another good reason is that by deforming the boundary of such a cavity, you can achieve unidirectional light emission. That means that the light goes out in a single direction. Yeah, this is shown here in the inset. Looks a little bit like the lights of a car, right? And that's, of course, with a circle, you cannot achieve this there because of rotational symmetry. Light goes everywhere in the plane. Here you can, with a clever deformation, the mechanism here is also due to chaotic ray dynamics, you can achieve directed light emission. Another reason is that when you have a microcavity, it's sometimes, if you want to bring in light, it's difficult. Yeah, because this is the time inverse process as getting light out. And if you have a large quality factor, it's difficult to get light in. And it's often done with waveguides. And it's most of the time only possible in a very narrow spectral regime. Yeah. Now, if you want to have a broadband, then it helps to deform the cavity, because there also the chaotic ray dynamics helps you to get coupling to the light for many frequencies. Then mode selection. So you see here in this micro ring, there is some small notches here at the side. I hope you can see this. Here's an experimental figure of the notch. And this notch kills you some of the modes, or many modes actually, in the sense that it makes the lifetime of the modes very short. And then they do not play any role anymore. Yeah. These are some. There are more possible reasons to deform a cavity. Maybe here's a good point to say, or to summarize what our group is doing. So we have actually two topics, I would say, but both are strongly related to optical microcavities. On the one side, we study light-matter interaction in semiconductor nanostructures that are, for instance, semiconductor quantum dots. And they are embedded in microcavities usually. And then we can study many particle quantum physics. Yeah, we have electrons, we have holes, we have photons, all of them are coupled. We can look in microlasers, in particular in photon statistics. Yeah, so you ask the question, so how many photons you get out? what's the probability to get n photons out, let's say. We study collective effects that can be super radiance or mode competition. And also recently became interested in studying the maximum entropy method in this context. On the other side, we look at what I call here complex wave phenomena in micro disk cavities. So we study there the already mentioned ray wave correspondence, directed light emission, which is here shown in this figure, weak boundary deformations. So boundary emissions which are so weak that you can use a perturbation theory for this, and non-Hermitian optics. In this talks, I will speak mainly about this non-Hermitian optics. I will also mention weak boundary deformations. Before I forgot, so here these are the people who contributed to this topics on this talk. So it's mainly my postdoc Guerricke, my PhD student Daniel Grom, and my former postdoc Shangwang Yi. And I also would like to mention Sebastian Klemm from Würzburg, with whom we have a DFG project on what we call integrated semiconductor platform for implementation of higher order exception. So I will come to this later. Okay, now non-Hermitian physics. So let's start. I mean, most of you are familiar with this, but let me start very simple with Schrödinger equation. Schrödinger conventional quantum mechanics. H bar is set to 0 to 1. So H is the Hamiltonian, and usually we solve this equation by solving first the eigenvalue equation for the Hamiltonian, right? And since the Hamiltonian is Hermitian or self-adjoint, let's ignore the difference between these two concepts, then we have some nice properties for the eigenvalues and for the eigenstates. The eigenvalues are all real. The eigenstates are all orthogonal to each other, and they form a basis, right? And the last property is important when you want to expand your solution of the Schrödinger equation in terms of these eigenstates of the Hamiltonian. Now imagine that the Hamiltonian is non-Hermitian. There can be many reasons for this, and I think in this seminar series there are already many things discussed. So one obvious thing is that you can have open wave conditions. That means your light or your waves go out and do not come back, right? And this gives you quasi-bound states, and effectively these are eigenstates of a non-Hermitian Hamiltonian. This is well known. Reactive decay is one example. Another class of systems where non-Hermitian Hamiltonians appear are an open system approach of quantum mechanics, where you have some system and you couple it to some environment. Most prominently, maybe the Monte Carlo wave function method, where we have explicitly a non-Hermitian Hamiltonian. On the theory side, let's say, on the experimental side, you can do post-selection also to reveal the underlying non-Hermitian Hamiltonian. Non-Hermitian Hamiltonians you also encounter when you study single or also 2-3 particle Green's functions in matter physics. They give you a lifetime of quasi-particles, for instance. Renormalization in quantum field theory, that's where PT symmetry was discovered. Also, linearization of dynamic systems around some equilibrium give you some linear equation which you can write in kind of Schrödinger equation form. And in optics, which we are now mainly interested in, we have radiation losses, absorption, and gain. This makes the system, the Hamiltonian, also the wave equation non-Hermitian. Let me just mention that when we speak about energy in quantum mechanics, we speak here about frequency. And instead of eigenstates, we speak about eigenmodes or modes, optical modes. Now, what are the consequences of a non-Hermitian Hamiltonian? The first is that the eigenvalues are complex in general. But that is okay, because if we look at the time dynamics, then we see that the imaginary part of this complex eigenenergy gives you a decay time, or growth time maybe also, or decay rate, let's say. That's fine. That is something we want to calculate. Then the eigenstates are in general non-orthogonal. Let me mention that here that actually non-hermiticity is not enough. Even so, we always speak about non-Hermitian physics. We should actually speak better about non-normal physics, because what we actually have to require is that the Hamiltonian is non-normal, meaning that it does not commute with this joint. if this is fulfilled, then the eigenstates can be non-orthogonal. And the last point is that the eigenstates may not form a basis. And the important question is this somehow common or exception? Right? To see this, one can do very simple-minded calculation, or can look at, for instance, this simple 2x2 non-Hermitian Hamiltonian. Yeah, it's just a kind of two-level system where the real parts of the energy are the same, but they have some difference in the imaginary part. Yeah, that's given by gamma here. Yeah, we have some coupling G. G is revalued, E is revalued, gamma is revalued. Now, and gamma describes losses. And you can do easy calculation, calculate the eigenvalues and the eigenvectors. We have here distinguished between right and left hand eigenvectors because the matrix is non-Hermitian. And I have here marked in red the square root of R. R just an abbreviation for G squared minus gamma squared. And I have done this, so because the square root we will encounter several times. And you will see that when we now send R to 0, for instance, yeah, just sending G to gamma, let's say, right? Then this not only the eigenvalues degenerate, but also the eigenvectors degenerate. Yeah. And it means that by doing this limiting case, we start maybe from two orthogonal eigenvectors, and then they become more and more non-orthogonal. At the exceptional point, they degenerate, they are collinear, and I can remove one of them because they're just linear, dependent on the other one. Yeah. Let me also emphasize that it's nothing to do with Hilbert space. So it's not that the Hilbert space is losing one dimension. It's just that the Hamiltonian does not form a basis. The eigen does not have an eigenbasis. Yeah, so this is written here. So this is an exceptional point, yeah, where this happens. Yeah, it's a point in parameter space at which two or maybe more eigenvalues and eigenstates of a non-Hermitian linear operator coalesce. Yeah. If only two eigenvalues and eigenstates coalesce, then we call it an exceptional point of second order. And we can generalize this to nth order, where exactly n eigenstates and eigenvalues coalesce. Yeah, notice this is very different from a conventional degeneracy, yeah, which you know from quantum mechanics, from Hermitian quantum mechanics, where only the eigenvalues coalesce, but the eigenvectors, they can always be chosen to be orthogonal. Yeah. This conventional degeneracy is called a diabolic point. The name comes from the diabol, from this juggling toy, which I hope most of you know. So it's, on the left, you see now the case for a two-level system. You see the energy eigenvalues as function of two parameters. And for almost all parameter values, we have exactly two eigenvalues. For instance, here, this one, that one, except at this point, this is the degeneracy point. This is called the diabolic point. Yeah? And very typical for this is this linear behavior around this diabolic point when you vary the parameters. Now, for exceptional points, the situation is very different because, first of all, we have to draw two pictures because we have the real part of the energy eigenvalues and the imaginary part. Then again, we vary two parameters here. This is non-exceptional point of order 2. And then we see this complex square root behavior. Yeah, this is exactly the complex square root of R shown in this example here. Yeah, it's very, very different from a diabolic point. This is not only mathematics, but it has been seen experimentally. And I think the first experiment on wave system has been done for microwave cavities by the Achim Richter group in Darmstadt, Germany. The first experiment on optical microcavities revealing an exceptional point is done by the Kyungwon An group. This is what is called a liquid jet laser containing laser active dyes. The details are not important, but just what they have done is they have measured the spectra as function of two parameters. And then they plotted this here, and then they see this square root. This is just the left picture. Yeah, this is always considered as a proof, experimental proof of an exceptional point in the given system. Yeah. Other examples, the many other examples in wave physics, let's say, are these exciton polariton billiards. Here's some more examples on microcavities. I just want to address the first one because this becomes important later. This is a microtoroid. where we have a diabolic point when the system is perfectly rotational symmetric. We have the degeneracy between one mode going counterclockwise and one mode going clockwise. And this can now be shifted to an exceptional point by these two nanofiber tips. Yeah, you can steer them around using some piezo elements. You just do it really by hand, do some knots. And you can bring this to an exceptional point. How this exactly works, we'll see later. Okay, for completeness, I also would like to mention parity time symmetry. Parity time symmetric systems are systems which are invariant under simultaneous application of a parity operation and the time reversal operation. Yeah, these are very special non-Hermitian systems, and they are interesting because they can have a completely real spectrum. Yeah, and if you want to do this in quantum mechanics in 1D, you have to have a potential which is invariant under a parity operation and time reversal operation. Parity transformation means just you replace x by minus x, and time reversal means complex conjugate. Yeah, in quantum mechanics, it's not so easy to do this. This can be done, but you can imagine it's difficult. In optics, it's very simple. Yeah, because the rule of the potential is played here by a refractive index. Refractive index can be complex because you can have gain or loss. Yeah? So, and then a PT symmetric arrangement is that you have a refractive index, it's here now in 1D, where the system is symmetric under exchanging x by minus x and by complex conjugation. That means by exchanging gain and loss. Right? Here's one example. So imagine you have two resonators, let's say. Let's imagine that I have only one mode, each resonator. One resonator has gain. I think that's the blue one here. One has loss, green one. They have exactly the same. So the loss is exactly the same as the gain. Just the sign is different. And if you want to describe this in the simplest way using such a coupled mode theory, the Hamiltonian looks like this. So you have omega as the frequency of the mode, should be the same in both cavities. You have in one disk, you have this gain, yeah, it's I times alpha, and in the other cavity you have the loss minus I times alpha, and you have a coupling G, which you get just by proximities. You have two resonators, they have some evanescent field outside, and they overlap and can lead to coupling. Yeah, and now for this simple system, if you calculate the eigenvalues, you discover that there are three different cases. So first, when alpha, so the gain or loss coefficient is smaller than G, then obviously this is real valued under a square root. So take the square root, you get a real number, so the frequencies are real. This is called a PT symmetric phase. Now, if alpha is larger than G, the frequency becomes complex. Right? You get some complex conjugate frequencies. This is called a PT symmetric, PT broken phase. And in between is an exceptional point. Yeah. And while you go from one phase to the other, you get a redistribution of mode intensities. Because, for instance, in the PT symmetric case, you get real frequency because there is an equal amount of intensity on the gainy resonator and on the lossy resonator. Yeah, that's because the frequency is real. Yeah, there's no net gain or not loss. So if you then cross the exceptional point and go in the PT broken phase, you get on one resonator more intensity than on the other, and this gives you effectively some gain or loss, some complex frequency. Okay. So now when people speak about non-Hermitian optics or photonics, they have the idea that they use these kind of non-trivial aspects of non-hermeticity, yeah, like this redistribution of mode intensities or like the non-orthogonality, to create some novel devices or novel device functionalities. Yeah, that's the idea of non-Hermitian photonics. And there are already several ideas around. Again, not a complete list. I just want to focus on that one with the sensors with enhanced sensitivities. There, the idea is simple. Use the square root. Yeah, the square root tells you, okay, if I vary parameters, I get some square root topology. Now consider a perturbation of your system as a parameter variation. Yeah, this can be always done. And that means if you perturb your system, you get, for the exceptional point, you get, let's say, exceptional point of order 2, you get a square root. Whereas for the corresponding diabolic point, let's imagine you can define the corresponding diabolic point, you get some linear behavior. And for small perturbation, the square root is always larger than the linear behavior. Yeah, that means if you look in your spectrum, you see that for the diabolic point, you get a smaller splitting than for the exceptional point. Right? That's the idea, to have enhanced, at least enhanced splitting, an enhanced response to perturbations. Yeah, this has been shown. This was work I have done with my experimental collaborators from Young's group with a whispering gallery microcavity, yeah, used for single particle dissection. And I will first, before I explain how this works, I will first now come to the first part, where I explain how you can achieve exceptional points in whispering gallery cavities. The first mechanism is what I call the asymmetric backscattering. Okay, now imagine the simplest possible case, a microdisk, where we have only two modes. One goes clockwise, one goes counterclockwise. And in a slowly varying envelope approximation, we can describe this by this, in a very simple-minded way, of course, by these two differential equations, where we just have the differential equations for the amplitudes of clockwise and counterclockwise propagation. And this can be easily solved to get a complex exponential, and omega 0 is the complex frequency. Now, of course, we can also write this in this way, right? And the zeros then indicate that there is no coupling between clockwise propagation to counterclockwise and vice versa. Now, this changes when we perturb the system. Now, for instance, we put here two dissimilar nanoscatterers close to the surface. Then we get a coupling of clockwise and counterclockwise propagation. And you may, at first glance, you may think this should be somehow equal. So the coefficient A and B should be equal, or at least complex conjugates of each other, because of Lorentz reciprocity. But this is not the case. Lorentz reciprocity requires that the diagonal elements are equal. In this case, we are here, I have to say, in the traveling wave basis, yeah, the basis of counterclockwise propagation and clockwise propagation. A and B can be different. So we just can, of course, call this a Hamiltonian, and then we have a non-Hermitian effective Hamiltonian, and we call the scattering asymmetric if the absolute value of A is different from the absolute value of B. Of course, this is only possible if there's no mirror reflection symmetry, right? Obviously. So if these two scatters would be identical with identical distance to the surface, this would not work. The most interesting case is, of course, what I call here the fully asymmetric backscattering. So B goes to 0, for instance, but A stays finite, or the other way around. This is the same. Yeah, in that case, we have an exceptional point. Yeah, because we find only one eigenvector, that one, and only one eigenvalue. Yeah, this eigenvector means in this case here counterclockwise propagation. So we have only one mode, and this goes counterclockwise. Yeah, this people also call a chiral state. Yeah, yeah. So the exceptional points always have some chirality, inherent chirality, and here you can see the chirality even in real space. So this can be seen, everything can be seen experimentally. So here's these microtoroid I mentioned already before, these two nanofiber tips, which here are indicated by these small scatterers. There is some relative angle between them. And you can probe the system by two waveguides where you send in light or you collect light. And then can you, for instance, plot, you can see the spectrum, you can see two peaks or two dips, depending on what you measure. And then you, for instance, can plot the splitting. This is for historical reason, it's called 2G. It's actually good to call it this way. So the splitting is function of this relative phase angle here between the two scatterers. And then you see that there are certain points where the splitting goes to 0. At the same time, you see when you plot the line width difference, that's something like the imaginary part of the splitting. You see also that they also go, I mean, roughly to 0. So these points are the exceptional points. Yeah, you can implement them in a quite dynamically controlled way, really by just rotating some knobs. You can also see all what I discussed before with the asymmetric backscattering, with the chirality you can see in the system. I want not to discuss this so much, but I want to now mention how this exceptional point-based sensor works. So the idea is, now you take this microtoroid with the waveguide, you probe the system, and you do it once for the diabolic point. This is with just the naked microtoroid, perfectly symmetric. You have two modes, clockwise, counterclockwise. The frequency is degenerate. You see one dip in the transmission spectrum. You probe the system with some test particle. This can be a real particle or it can be a third nanofiber tip. And then you see, is because of this perturbation, you see splitting. And you do the same for the exceptional point. Yeah, this is by first install the exceptional point using two nanofiber tips. Then you come with exactly the same particle than here, and you see a larger splitting. How can we be sure that it's exactly the same particle? We do it this way. We come from here. We implement first the exceptional point, come with the test particle, and then remove the two nanofiber tips. Then we are here. And we can see that the splitting goes down. Yeah. Here the effect is, it's a proof of principle experiment. The effect is not big. That's a factor of 2.5 enhancement of the splitting. But it's in principle, it works. Yeah. There are meanwhile other experiments. One with an EP3, so an exceptional point of order 3. And there they have seen an enhancement factor of 23. Yeah, that's quite a lot. I like this experiment here with a rat, where they have implemented such an some kind of remote wireless system, implemented such an exceptional point-based sensor in the stomach of a rat, and they can measure then the breathing rate quite accurately. It's also important to mention that there are some works which question that these are really good sensors because of the signal-to-noise ratio. So if you do some analysis in certain systems, I mean, broad cloud of systems, then you discover that the noise is also enhanced. And it can be in the same way than the signal. Yeah, that means the signal-to-noise ratio is not enhanced at all. Yeah, this was done here in the group of Valhalla with some gyroscope system. But also recent experiments have shown that in other types of systems, you can achieve an enhanced signal-to-noise ratio systems. Now, if you're interested in these kind of systems, I have also written a review recently, which contains most of these things. Okay. Now, I would like to come to another mechanism to create exceptional points in Wiersig and Guerricke cavities. And this is the coupling of modes with different angular momentum. What I mean with this is, I mean modes with a different azimuthal mode. So consider these two modes in a perfect circular disk. This has azimuthal mode number 22. This has 18. But they have similar frequency because the radial quantum number or mode number is different. Yeah. So let's assume that this is the case, that they have a very similar frequency. So we start with two modes with similar frequency. X is, by the way, just a dimensionless frequency. It's k times r. K is the wave number equal omega divided by c. C is this number. So in such a situation, we cannot try to couple these two modes by a boundary deformation, which is weak. Yeah, because they're already nearby in frequency space, so a weak deformation should be enough. And for weak deformation, there is a perturbation theory that tells you when the boundary is in it's a circle plus a small deformation function. Yeah, phi is here an angular is an angle, polar angle. R is the polar radial coordinate. So if this function is small compared to R, then the perturbation theory can be used. I skip for almost all of the details. I just mentioned that at the end of the calculation, something very, very simple appears, namely an effective Hamiltonian, where the x1, x2, so the two-dimensional frequencies appears, and the a's here, which are Fourier harmonics of the deformation function, essentially a Fourier transform of the deformation function. This is here for positive parity. You can also have negative parity. Yeah, so this is an explicit 2x2 Hamiltonian. You may say, oh, just 2x2 Hamiltonian. But remarkable is that everything is now known. Yeah, so that's different from the usual situation. When people use coupled mode theory, they have the philosophy of saying, okay, I have a resonator here, each have one mode, they have a certain frequency, they are nearby, so they have certain coupling strengths. That's it, right? And then the parameters will be varied. Yeah? Here we have all the parameters explicitly given in terms of the modes of the unperturbed system and of the deformation function. And by the way, the meaning of this effective Hamiltonian is that the eigenvalues are the frequencies, your eigenfrequencies of your system that you're looking at. And the eigenstates give you the contribution of these original two modes. Yeah? Okay, so now one example is actually these two modes with a certain refractive index. One can, by looking at the Hamiltonian a little bit longer, you find that this is a good deformation function. So it's a sum of two cosines function with different period. You get two deformation parameters, epsilon and sigma. And you believe me, everything can be done with this analytically. You get analytic equation for the critical deformation parameters where the exceptional point happens. And the most important thing is that these numbers are very small. Yeah. So R is, so they are, so in terms of R is the radius of the cavity. So they are more than 1,000 times smaller than the radius of the cavity. So it's a very, very weak deformation. So you cannot see it when you look at the cavity. So here's a mode, the mode at the exception point. Yeah, only one mode, even so we started with two, that's the exception point. You see, I'm not sure how good you can see it. You can see the boundary curve, this white line, and you cannot distinguish it from the circle, right? But still it gives you an exception point. And the good thing is, weak deformations usually, I mean, they preserve the quality factor. Yeah, a strong deformation usually destroys the quality factor. Not always, but most of the time. And you want to have a high quality factor for experiments, right? So potential large quality factor for a very weak deformation. Now here's just a comparison to experiment. So here's the real part of the dimensionless frequency, here the imaginary part. Here's the one of the parameters is varied, the other one is the sigmas keep fixed to this value. PT here means perturbation theory. Sorry for this. BEM means boundary element method, so it's a numerical scheme to compute the modes, I mean, fully numerically. And you see there's a very nice agreement. You can see that there's also the square root here and here. Yeah, so this works very well. Now one can go further now and can do this for three modes. Yeah, you can look at situation where you have three modes with a similar frequency. You can fine-tune possibly the refractive index. Yeah, theory, this can be done, but there are also experimentally certain possibilities. And then I skip all the mathematics here. I just show you one result. So here is the deformation function as function of the polar angle. And you see it's quite complicated function. That's nothing you can guess, right? Can that also difficult by playing around. Here, look at the prefactor, it's 1,000. So it means, again, this is a very, very weak deformation. So again, I guess you cannot see the difference to a circle. This is the mode in the microcavity. Yeah, it's only one mode. We started with three. We are at an exceptional point of order 3 now and get one mode out. On the right-hand side is the real part of the frequency as function of 2 of the, I think, in total 5 parameters. Here's the imaginary part, and yeah, experts see that it's a cubic complex, cubic root. And of course, if you can do 2 and 3, you can also try 4. We have done 4. But there's a twist. The twist here is that in this case here and in the previous slide, we have always used a perturbation that does not break the rotational symmetry. That means we couple clockwise and counterclockwise perturbation always in a symmetric manner. Now we can do this, can break out to this symmetry, and we can couple them in total 4 modes. So if you look at this, if you look at the other 2 parities, there are actually 4 modes. We can couple all 4 of them by using a clever perturbation that you can see if you look at the 4x4 Hamiltonian, and this also works. Okay. Now, the third scheme, waveguide coupled microwaves. let me first start with a paper of Rami Al-Ghanaimi's work. We have shown that this here is at an exceptional point of order 2. A simple microring coupled to a waveguide, which is semi-infinite and has a mirror here. This is what I called in previous slides fully asymmetric backscattering, because if your mode goes, let me think, counterclockwise, it can couple out here to the waveguide and just disappears to the left. It's just a decay channel. If the mode goes clockwise, it can couple out here. It goes here to the right and is back reflected, at least partially, at the mirror. It can go back to the cavity, but in the opposite direction. So there is a backscattering from, let me think, from clockwise to counterclockwise, but not vice versa. So fully asymmetric backscattering, exceptional point of order 2. Now the really fun thing with this system is that the existence of the exceptional point does not depend on various parameters of the systems. For instance, the distance of the ring to the waveguide doesn't matter. Yeah, it only should be not too far away, and it should have some coupling at least. Yeah, right. And also the size of the ring doesn't matter, right? All of these parameters do not matter. And if I now plot for all of these parameters, plot the exceptional point in my full parameter space, I end up with a surface or hypersurface or line, depending on the dimensions, where all points are an exceptional point of order 2. And then the clever idea is try to keep all the fabrication intolerances inside the surface, the exceptional surface, how is it called, and all the things that you possibly want to sense, all the perturbation you want to sense, they should somehow go perpendicular, or at least not inside the surface. Right? And this way, you can combine a strong spectral response and robustness of the exceptional point. Yeah? Normally, it's very difficult to achieve an exceptional point experimentally because it is so sensitive to perturbations. Here, you can combine these things. And so this is a great idea, and our small idea was then, okay, if you have one ring, why not 3? Or 2, 3, 4, 5, 6, right? Okay, this is our idea. Okay, so we start with, let's say here in this example, 4 rings, here 3 rings. These are COMSOL, I show you COMSOL calculations. The mirror is here realized by a small gold mirror. Here's actually one exceptional point eigenstate. Now let's perturb the system. Perturb it with some particle here, in the sense of single particle detection, and see what's happening if you increase the size of this particle. So what happens when we increase the perturbation? And we see the following. If we have 4 rings, or let's say, if we start with 1 ring, this was the original proposal by Rami here, then we see a square root splitting. So here is the delta omega is the splitting. Splitting is more complicated if you have a higher order exception point. But you see a square root dependence on the perturbation parameter epsilon. If you have 2 rings, you get an exceptional point of order 4 splitting. If you have 3 points, exceptional point of order 6, and 4 rings, exceptional point of order 8. Yeah, you can see the systematic, of course. The order of the exceptional point here is 2 times n, when n is the number of rings. Yeah, so and this is also an exceptional surface, yeah, because it doesn't really matter what the distance of each ring to the cavity is. Yeah, it should be close enough to see some coupling, but it doesn't depend on the fine-tunings. No fine-tuning needed. And you have a robust construction of higher order exceptional points. Yeah? Can be done, exceptional point of order 8, easy, right? There's no fine-tuning. Here's a slightly different example, but the physics is more or less the same. What we have here is the corresponding EP eigenstate. Note that not all the intensity is concentrated here on this ring. There's also some intensity here. You can possibly see this. Maybe you can see even here, but it's more difficult. Now, we have done the following. Let's imagine for 1 second that we put some scatterer, some test particle only here at the lowest ring. Then we see the full 8-order root. So we see what we would expect. So this is an exceptional point of order 8. And we see what we would expect. But if we place the test particle here or here, we see a lower root. Yeah, for instance, here we see only epsilon to the power of 1/6. Yeah, and here, if we put it in the top, we see just the square root behavior. And we can explain these cavity selective response, which possibly is useful because it tells you where the particle attaches to the microcavities, has to do something with generic and non-generic perturbations. So an exceptional point of order n shows only a 1/n scaling or splitting when you have a generic perturbation. Usually that's enough to know what you want to have to know, because non-generic perturbations are somehow of measure 0 in your parameter space. But in these kind of systems, not the case. Right? They can very natural to put a scatterer here, and this gives you a non-generic perturbation. Okay, here's some experimental figures. So everything I showed here was numerical calculations. Experiments are coming soon. Yeah, so you see already some first sample of Sebastian Klem's group in Würzburg, and maybe next time we see, I can show you some experimental results. Okay, time is running, so now I come to the question of how strong an exceptional point is. Now I told you the spectral response and exceptional points in terms of splittings is larger for an exceptional point than for a divergent point. Now we can ask the question, what if we have two exceptional points of the same order, which one shows the stronger splitting? Of course, for a given perturbation, I can just do the calculations and have the result. But let's imagine I want to make some general statement without knowing the perturbation. I just want to say it's kind of generic perturbations, nothing special. And that means then that can I assign a number to an exceptional point to quantify a spectral response? Yeah, can I give them some here, this one here number, which is then larger than the number that I give to this exceptional point? And the answer is yes, one can do this. It's this inequality. The left-hand side is the splitting or the energy change of the eigenenergy, how they change with respect to a perturbation, absolute value to the power of n. And this is bounded from above by a product of two factors where the first factor, the blue one here, depends only on the perturbation, and the other one depends only on the exceptional point. And the latter we call the spectral response strength psi. Yeah, so this is the quantity that we can assign to each exceptional point. And it tells you how good the exceptional point is in the sense of how strongly does it react to perturbations. Now, how to calculate this quantity? It's very simple. If the Hilbert space dimension equals the order of the exceptional point, then what we have to do is we have to calculate this matrix n, which is the traceless part of the Hamiltonian. Yeah, EEP is the eigenvalue at the exceptional point. HEP is the Hamiltonian. N is then the traceless part, capital N. So we have then to make to calculate the power of n to the power of n minus 1. Now n, small n, is the order of the exception point. And take then the spectral norm. Spectral norm is nothing else than the maximum singular value of this matrix. You can do the same for the other function, but it's actually not so interesting. Yeah, so I have an easy way to calculate the spectral response strengths. Note that the mathematicians, they know this concept actually, but it's kind of difficult to assess for physicists. So my approach, I claim it's much easier, mainly because it's in terms of the Green's function. I don't go into details here, but Green's function appears everywhere in physics. So this is then quite straightforward for physicists. So just two examples. Consider this Hamiltonian, which we encountered when we discussed these asymmetric backscattering, fully asymmetric backscattering. Here, for instance, microtorah with the 2 nanofiber tips. If we do the calculation, it's very simple, 2x2 matrix. We get that the spectral response strength is the absolute value of A. A is the backscattering coefficient. That means if we want to increase the spectral response of our system, we have to increase this internal backscattering by some means. Here is a EP3 example. It's a PT symmetric system, 3 rings. One has gain, that one has an equal amount of loss. One is neutral, they're coupled. Yeah, here's kappa, here's, I call it G. Yeah, so this is the Hamiltonian. If alpha is this G times square root of 2, then this is at the exceptional point of order 3. If we do here the calculations, we find that the spectral response strength psi equals 2 times alpha squared. That means if we want to enhance the spectral response of this system, yeah, so make the square root steeper, so to say, we have to increase the gain loss constant. We have to make alpha larger. Of course, at the same time, we have also to make G larger because they have to keep this relation. Okay. Let me also mention that this quantity psi not only describes the spectral response to perturbations, but also other things like the steady state intensity response to excitations. So for instance, if we have such a system here, we excite it by some harmonic excitation with a frequency omega EP and some pump strengths P, and then look at the total intensity of our system, we find that it's bounded by this product of these three factors. The first is, not surprisingly, the pump strengths. The other one is the non-Lorentzian spectral response, let's say. And then this spectral response things psi. So the same quantity psi appears also here. It tells you how strong the steady state intensity response is when you pump the system. Also, a dynamic response to initial deviations from the EP eigenvector can be quantified with the same quantity psi. Let me also mention that for passive systems, one can show that there is an upper bound also for the spectral response strengths, meaning that the passive systems, they have some limitations. There are some inherent limitations that you can avoid by using systems with gain. One can also draw some conclusions for systems that are not exactly at the exceptional point, but nearby. Yeah, nearby, you would describe the eigenstates usually with Peterman factors, and one can show that the Peterman factors are directly related to the spectral response states. And finally, if the Hilbert space dimension is larger than the order of the exception point, is of course the general case, one can extend the theory and can use it also there. Okay, I think. Let me come to a summary. So first part, I gave you an introduction to microcavities, to exception points, and I hope you find also, like me, that it's interesting physics with potential applications. Then I discussed three mechanisms, let's say, to achieve exceptional points in whispering Guerricke cavities. This is asymmetric backscattering, yeah, where we get some scattering from clockwise to counterclockwise, but not vice versa, or the other way around. Then coupling of modes with different angular momentum by a small boundary deformation, and then these waveguide coupled microrings where we have one waveguide and mirror that introduces essentially also asymmetric backscattering. And at the end, I described these spectral response strengths that tells you how strong your exceptional points react to perturbations, also excitations, and also to initial deviations from the exceptional point eigenvector. Yes, with this, I would like to come to an end, and I would like to thank you for your attention.
Thank you, Jan, for the very nice and didactical talk. We are now open to questions. I see Lorenzo has a question. You can mute.
Yeah, no, I was just clapping, sorry.
Okay, sorry.
Okay, thank you.
Okay, so if no one has questions, I have a small curiosity to ask. So what type of applications you see for this sensing? Because I saw that you show a plot that you show how like the size of a scatter particle influences, the behavior of the system.
Yeah.
But what type of like quote unquote real life applications you expect for this type of like micro resonators?
Yeah, so let me just mention. So there are for microcavity sensors, where you monitor the change of frequencies, is already a commercial application. So there are companies, for instance, which produce several of these microtoroids. They functionalize the surface with some chemicals such that only certain types of particles bind to the surface. Yeah, for instance, certain types of mRNA or something like this. And they have a matrix of microcavities, and each microcavity shows a different response. Usually, that people do this with a change of frequencies. Yeah, just we look at a single dip or peak and how it's shifting by such a perturbation. Yeah, so you can use it to, for instance, yeah, it's commercial for blood, for instance, if you want to analyze blood for certain diseases, cancer maybe. You can already do this. I mean, the first commercial application, or some person from a company I have spoken to, this is already at least 10 years ago. But of course, just looking at only how one single frequency is shifting is a bit problematic, because I mean, all sorts of influences can lead to this, right? Because if you have a small temperature change, because the effective index is slightly temperature dependent, also the size of the cavity, of course, can slightly change when you increase the temperature. So all of this change the frequencies in kind of uniform ways. So we have to keep track of this. So it's better to look at splittings. And what people have done also a lot is to look at splittings, which arises at diabolic points. Yeah, they never called it this way, but this is kind of standard thing. So they try to make cavities as perfect as possible to get a degeneracy between clockwise and counterclockwise propagation. And then they look at the splitting. Now here you have to go to an exception point, and you can look at the splitting. So I think this can be used commercially. Of course, there are some certain issues which make it then again difficult, because if I implement the exception point like in this experiment, so when I put 2 nanofiber scatterers or 2 nanofiber tips, of course I introduce additional losses, right? Obviously. So this makes the line width a bit broader. You can see this here on the left-hand side. This is of course a drawback, right? It's better than, okay, to have maybe a smaller line here and less splitting. That depends really, right? But I told you also one can achieve with small deformations, you can achieve exception points. This may be a better way. But I think, yeah, so I think to summarize, I think these sensors can give you some applications, real world applications.
I see, thanks. Clara, you had a question you can ask. Then after her, we have Lavi, and then a question in the chat that I will read. Please.
Yeah, thank you very much for this really exciting and interesting talk. I was really interested in the spectral response strength that you showed towards the end, and in particular, I think on the last or second to last, yeah, exactly here. This looks like you can also say something about the bandwidth here, right? Just through this.
Yes, I mean that the response of the intensity due to some excitation is non-Lorentzian, is of course well known, right? Everybody knows. Here it pops up in this formula also quite naturally. You can, so the spectral line shape comes out here very naturally, and you can say something about the bandwidth. Yes, you can do this. I mean, the larger n, the more broader.
Yeah, I was just thinking, if this, I mean, you can also have exceptional points in direction amplifiers, for example, and then this could say something about gain bandwidth product or something like that.
Yes. You know, you're referring to the work of Rami Alganani and Anja Mittelmann, right? And yes, so I think this can be helpful indeed. Yeah, I have spoken to Anja Mittelmann, and we want to look together on EP3s. So because for EP2s, you can essentially write it down, can do the full calculation, but for EP3s or higher orders, it's difficult, and this is a better approach. Yeah, so this can be useful. I agree.
Very, very interesting. And is it also possible to generalize this to, I don't know, take the noise into account, or are you thinking about this?
Yeah, it depends. Yeah, this is actually a good question. So there are two sources, two kinds of noise, right? One is where you have some noise in some input signal, and you look what is the noise in the output signal, or you could also put some noise in the parameters of your system. So they have some fluctuating parameter, some parameters in your Hamiltonian. So I think the quantity psi plays a role in both cases, but I cannot show you an equation, so some final result, but I think it can play a role in both cases. But I cannot give you now for a specific system good yeah, some final result. But I would guess that if you look careful there, you can find this quantity there as well. Yeah. So please,
Yeah,
please
very
have a look.
interesting. Yeah. There are more questions, so thank you very much.
Yeah. So Lavi has a question. You can mute yourself. Go on, please.
Yeah. Hi, Jan. So thank you so much for this nice talk. Actually, I have a question on the part where you were talking about the coupling of the micro ring resonator with the waveguide, and then you were saying that you could generate the different orders of this different. Yes, exactly. The energies could have a different power dependence. So so one thing which was not super clear to me, that how could I intuitively think, because what I was thinking is that you have this one micro ring resonator and then you have a waveguide, and because of this extra mirror, I'm trying to generate an asymmetric coupling. So as the result, so that's how I was picturing. Then I was not able to understand how this different exponential power could be seen from this simple Hamiltonian where I have this asymmetric coupling. So I just want to have this understanding. And just one part to it is that is it possible that I could have seen the similar physics without coupling this it to the waveguide, this planar, this straight waveguide? Instead, if I would have used some nanoscatterers, like I just put them and I'm able to generate this epsilon 1/4, epsilon 1/6 merely from these nanoscatterers, would it have been possible? So this is
with one ring and some scatterers, or with several rings?
No, with one ring. If I understand well how you generate the different powers of the energy. So with the one ring, I was thinking with the different nanoscatterers, different amount.
No, so if you have one ring, okay. Let's assume that you are looking in a frequency window where you have only two modes, right? Left, clockwise and counterclockwise. Then of course you can never achieve more than an exception point of order 2, right? Because it does have not enough modes to couple.
Yes.
But clearly, I mean, in such a cavity, you have, if you look at a broader frequency window, you have possibly many modes. And in some sense, what we have done here is in this spirit. They're not point scatterers, but boundary deformation. You can use, for instance, to get this kind of cavity for 4 modes, or maybe even more. This is possible to have in the single cavity more than an EP2. Yeah?
Okay.
You could, in principle, also do this with scatterers. Yeah, but you have to start from the beginning. It's from a situation where you have already several modes spectrally close together, such that you can couple them easily. But it's it's not trivial, right? It's not trivial to do this with scatterers. Already with 2 scatterers for an exception point of order 2, you have to fine-tune the size of both scatterers and the distance to the cavity. I have to play around in principle with 4 parameters already. I mean, finally 2 are enough, but you have in the beginning you have 4 parameters. And if you want to do this now, such a situation with 3, 4 particles, it becomes really a mess. I mean, here we have done finally, after we have setting up this deformation function, we can do a brute force search, just because we have derived an the effective non-Hermitian Hamiltonian. We could never do it with the full calculations. Here, I think, I'm not sure how many. I think here we have 12 parameters or so, but we can, because it's just a 4x4 matrix, we can find the exceptional point. We cannot do it fully numeric. So if we would have to do this with scatterers, we possibly have to do it fully numerical. That's difficult. Okay, now back to this question. So here I try to explain the EP2, right? EP2 comes just from the fact that there is the Hamiltonian, the effective Hamiltonian looks like that one with a 0 here, right? Just because there is only scattering from one to the other, there must be a 0 here. This is then similar to a Jordan normal form. This is an EP2. Now, if you do this for many micro rings or several micro rings, you can also write down effective Hamiltonian.
I see.
You can try to determine the coefficients by by comparing it to full calculations. And we have done this. And then you find Hamiltonians which have some diagonal elements, they're all equal. And then you have only on the next non-diagonal, next diagonal, you have non-zero coupling terms. So this is also like a Jordan normal form. I mean, the Jordan normal form has always ones, right? The next, just above the diagonal. Here we have something, but it's clearly an exceptional point. And to see this, one has to write down an effective Hamiltonian. You have to say, okay, when I rotate here, I can go out, I can couple here in. I cannot couple here in, right?
Yeah.
I rotate this way. And if you think about this and write down some Hamiltonian, which is mapping this, then you see, oh, this is a kind of similar to a Jordan normal form. If you look at our paper, you can see this Hamiltonians. So maybe then maybe have a look at this and then you see how it works.
Yeah. I mean, it becomes clear, like as you increase the number of rings, the size of the matrix is also increasing with it. So as a result, you could get the higher order exceptional point, if I understand it well.
Yes.
Because I can see that the different terms will not couple. Different terms will not couple, and it's like I'm just generating a Hamiltonian, or let's say the matrix, which only has this off-diagonal elements which are non-zero. That's how I see.
Yes. Yeah. It also looks similar to the Hartano-Nelson model, actually. If you unfold this in some sense.
Okay, I see. Okay. Thanks. Just one very last question. Like when you were talking about this.
Sorry, maybe it's better that we move on. There are other people in the list. If you can wait, maybe if we have time, like at the end, we can go back. That's fine. Okay. Thank you. So someone asked in the chat, can you please tell me the difference between working at an EP and work near an EP? If you want to unmute yourself to elaborate a bit more on the question, you can do it. Otherwise, if Jan can.
Yes, I can try to explain.
Hello. Hi, Ian. Thank you for your nice talk. This is actually my question. That is, what is the difference between working on an exceptional point and working near or around an exceptional point?
Yeah, I mean, maybe this pictures can explain a bit. So here you see the splitting, which is calculated or is defined in this way. So if you're an exceptional point, you have, let's say, 1, 2, 3, 4, 6. This is an EP6, this cartoon here. If you're the LP, you have really a single mode. You see only in your spectrum, you see just one peak or one dip, depending on what kind of spectrum you look at. Now you perturb the system, you see how these 6 eigenvalues explode in some sense. And they, for an exceptional point of higher order, they really go far very quickly. For small perturbation, they go really far apart. Now, if you're not exactly at an EP, then you already start with some splitting. For instance, here in this numerical calculations, 10 to the power of -8 epsilon. This is really, really small. Yeah, this is 10 to the power of -8. I take the square root. That means the radius of this small particle is 1,000 times smaller than the radius of the disk. So it's already a very tiny particle. And you see already a splitting, right? Splitting is not zero. So in all real experiments, in all real numerical calculations, you never are exactly at exceptional point. Even, I told you here, this is an exceptional point of higher order, there's an exceptional surface, but still there are some effects which drive you slightly away. For instance, here, there is some kind of internal backscattering which has to do with the fact that the waveguide is nearby. It's a very weak effect, but the exceptional point of high order is amplifying this strongly. And that's why you see already some splitting here, right? And splitting is of the order 10 to the power -3, -4. That's already quite a lot. So even if you do not do the full calculations here, but start with a Hamiltonian, let's say, very simple-minded, very close to Jordan normal form, you see already, if you do the numerics with Maple or whatever, you see already a strong splitting. Yeah, because even tiny numerical errors are amplified. So you are never really at the exceptional point, but nevertheless, you see these strong enhancement of the splitting, right? You can, wherever you go here, I see that the dark blonde one here from the EP8 is larger than that from the EP2, much larger. There are many orders of magnitude. So there's no need to be exceptional point, but at some point, if you're really far away from the exceptional point, at some point you see these saturation effects where suddenly even the EP2 gives a larger splitting. But if you are sufficiently close to an exceptional point, you still see a large response. Yeah.
Yeah.
If this
Yeah,
answers
I
your
understand.
question.
Yeah, I understand. And I see that the difference between this epsilon to the power 1 by 8 and 1 by 6 is very small. So as you go on increasing your order of the exceptional points, you must be more and more near to it, I suppose.
Yes. This is the price you have to pay then, right? Yeah. It becomes increasingly more difficult. Yeah.
Yeah, yeah, I understand. Thank you.
Thanks. Matteo, now you can ask your question.
Hi. Thanks for the nice talk and also for answering all our questions now. I was wondering, when discussing the sensing, you briefly mentioned conditions for which the signal-to-noise ratio is enhanced versus conditions for which the signal-to-noise ratio is not enhanced. And I was wondering if you could briefly elaborate on that, please.
Yeah. So I can tell you what these two groups have done more or less. I think I missed it, right? Yeah. Okay. So here the Valhalla group has some gyroscope where they have two lasing modes and they have some non-reciprocity because of this effect of rotation, right? You can show that this gives different, distinguished clockwise and counterclockwise, obviously somehow, yeah. And the problem with the experiment, I mean, it's a very, very clean, nice experiment, but the problem is that I think that they have the modes that they use are also lasing modes, so they lace in that sense. So they have a laser gyroscope, and there you see all kinds of noise, and this is amplified at the exceptional point. In exactly the same way, yeah. Now the experiment here where Sampikos Kotos was involved, they have done something different. They had some system, I mean, the sensor, the thing that they sense is very different. But what they have done is something interesting. They have a system with a coupled to a waveguide. And it turns out that the effective Hamiltonian describing the system with waveguide is slightly different than the system alone. Now what they do is that the system with the waveguide, they drive to an exceptional point. But the coupled system, let's think about it as a cavity, is not exactly the exceptional point. So that turns out then that since you're not exactly the exceptional point, the noise in the cavity is not so much enhanced compared to the signal, to the splitting that you see in the waveguide. And the waveguide is what you naturally measure because you study the signal, which is what comes out from the waveguide. So in that sense, they somehow decouple the signal enhancement, or the splitting in this case, and the noise enhancement. Of course, this is somehow also a bit delicate. They have to, of course, because the waveguide is kind of small perturbation. They are always, the cavity always is close to an exceptional point. So it's a kind of compromise that you have, but this works. So this gives you a clear enhancement of the signal. Let me also mention that all these issues are mainly relevant for quantum noise, I would say. I mean, if the technical noise is small, then that doesn't really matter. I mean, you always see a very nice large splitting, right? As I said, it can be more factor 20 in experiments. So then the noise, the quantum noise is not, if you don't have quantum noise and the technical noise is not so high, then you see very clear splitting.
Thanks a lot.
Okay.
Thanks, Jan. I see that we are here more than an hour and 10 now, so I say we close our session for today. We thank all the participants, and we kindly remind you that next week we will have Benedetta Flibus. Hope to see you then. Thanks a lot, everyone. See you next.
Okay, so thanks a lot. Bye.